Okay then, so if we look at natural loads then, the loads that occur from nature, they can take several forms, and we dealt with in the previous slide the gravity loads, so the loads of a person sitting on a chair, the weight of the chair itself. So those are the variable gravity loads, and they find their way into the structure through the floor slab, for example. Now that floor slab has its own self-weight under gravity, and that's a permanent gravity load. So again, the gravity of all the roof structure, the walls, the ceilings, the wall coverings, they all have mass, and under acceleration due to gravity, they exert a force or weight onto the structure, which, as we saw in the previous slide, has to find its way through a load path down to meet a reaction. So if we have anywhere on the Earth, so the Earth is an object with huge mass, and anything in the building that we're designing, which might sit at this part of the Earth here, will have a tendency to will be accelerated due to gravity towards the center of the Earth by virtue of the fact that it has a mass. So anything with mass will exert a force within the structure acting towards the center of the Earth. And we saw in the previous slide that load path has to be competent to get it to a point at which that can be met by a reaction. So the total loads in this downward direction have to be met by a reaction force which is equal and opposite, in order for that structure not to move under the load, or to accelerate under the load. But there are other loads other than just the weight, and again they all have to find their way through a load path, and they may come down, and again this reaction has to increase to match the combination of all the loads from gravity and other sources. So other sources might be aerodynamic forces on the structure. So if, for example, we have a portal frame building with walls and roof, that building is in an environment where there is airflow around that building, which is wind basically, and those particles of wind have a mass, and they are deflected so that their velocity is changed either by it being slowed down or stopped, or being deflected, change in direction as a change in velocity. So that acceleration will exert a force. Force is mass times acceleration. So the building that we're designing, the civil engineering structure that we are designing, will see a force from that wind loading, and that force on this wall will typically act perpendicularly to that wall. You will also see a force acting perpendicularly to this roof element here. On the leeward side of the building, you would tend to get suction, so you'll get partial vacuum or vortex shedding, which would generally lead to an uplift on this element of the roof and a suction on this back of the wall here as this airflow aerodynamically flows around the building. So one of the significant load cases for many structures will be the wind loading on that structure. Similarly, earth pressures and water pressures. If we have a pile of sand, granular material, so that sits on the ground, that will have a natural angle of repose, which might be typically 30 degrees. And that is the angle at which the granular material can support itself. Now, if we choose to cut that natural slope at this point here by our building, so for example, if we have a basement to this building that we're designed, and that basement goes below ground level, so we're down at a sort of formation level here, there will be earth pressures, and those earth pressures are essentially, if this is the retained part of the fill, that gravity will cause the earth in this region here to exert a force that acts down on the wall in this direction here. So we will get forces at this point and this point due to earth pressures. So again, we will have to design this building for these earth pressures. Now, we might also have a water table, subterranean water table at this level here. So we will have to design this building for the water pressures, and those water pressures will be hydrostatic, so they will increase with depth. So we'll get a triangular load which can be resolved as a force acting in this direction, and we will also get typically an uplift on the basement floor, which is trying to push this floor upwards due to the water pressures again. So similarly, the water table would typically be the same on both sides of the building, and we will again get a water pressure on this side. These earth pressures and water pressures obviously are either here or they're not. They can be present. The water table can rise up or down, and the wind can drop off to zero or be at its full design load. And that design load is set out in the codes of practice as a return period event. So it might be the 150-year gale event or hurricane event. And again, different buildings are designed for different return periods. Different statistical models are applied depending on what code of practice you're designing to. And we will come on to look at different codes. Well, we'll come on to look at one particular code of practice, the Euro codes for structural design. Coming on to temperature loads, if you have a two bridge abutments with a simply supported structure, simply supported bridge deck, that bridge deck will be subject to temperature variations, and those temperature variations might, for example, between summer and winter go down to minus 10 degrees for argument's sake, and go up to plus 40 degrees Celsius. So we might have a temperature range that we're designing this bridge slab, which are of the order of 50 degrees. And typical construction materials that we would use in a bridge, so steel and concrete, they would typically have a coefficient of expansion under temperature load that might be typically 12 microstrain 12 microstrain per degree. And what that means is that for every degree change in temperature, that we will get an extension which is 12 microstrain, which is a fraction of the original length. So if that's the original length of our deck, as the temperature rises for each degree, a certain percentage of that deck length will be the amount by which the deck increases its length for a positive change in temperature. Now, for longer spans, so typically for most bridge structures or some of the longer buildings, it's necessary to accommodate that expansion, because that expansion can get quite big. It's obviously a function of the original length. So for longer span structures, this delta value here, this delta here, can be quite significant. And the problem that you've got is let's say that delta is 25 millimeters for a bridge deck that we might be designing. That bridge deck is trying to expand by 25 millimeters. Now, the forces that are involved in that expansion, if you try and resist that expansion, are phenomenal. They are essentially equivalent to the force required to compress this deck by 25 millimeters. And, you know, these are big structural elements. They have quite high stiffnesses, big, you know, in terms of the Young's moduluses involved. We need really big loads to compress a bridge deck by that amount. And the consequence of that is that these abutments just aren't capable typically of providing that kind of resistance. So the reaction that you're requiring these abutments to provide to resist that expansion are just not capable of being designed very easily. Occasionally we do, well, we typically do look towards something called integral bridges in bridge design now, but traditionally, for example, and in most longer buildings, we don't even attempt to resist those loads, because what happens is that this structural element will fail, and this will crack or bend under the extreme loads from this temperature induced expansion. So traditionally what engineers have done is to fix it at one point and then allow, by putting roller bearings or elastomeric bearings or some kind of movement device which just allows this bridge to expand and contract under temperature. So although we recognize that there would be a load with temperature, we're usually designing for temperature effects by detailing the structure such that these loads don't come to light. So although we can work out that this would undergo 12 microstrain per degree under temperature variation, we might choose, instead of trying to resist it at the abutment, to allow it to move. And typically for longer span bridges, we would design it to be capable of moving, such that that load just doesn't come to light. On some of the shorter spans, we would design these potentially as an integral bridge, but then we would need to make sure that we provided sufficient competence in this substructure to deal with that kind of load. And even then, integral bridges, although they might not have bearings and joints, they will still be flexible enough to give and take in terms of allowing that movement to happen, rather than straight out resisting that force. Seismic loading is basically earthquake loading. So earthquakes on a structure will tend to vibrate the structure at a particular frequency in either a horizontal direction, occasionally a vertical direction, or some combination of the two. And the frequencies and degree to which vibrations occur is a function of the location, the type of seismic event that a particular geographic location we'll see. In the United Kingdom, we tend not to have to design for seismic. There are certain situations where we would for long span bridges, for example, particularly where they're crossing, as they quite often do, by virtue of the geography. There might be a fault line, for example, that the bridge crosses, and that might be why there needs to be a bridge there in the first place, because you're crossing a natural, if you like, change in the geology. So a fault line might have a river, for example, might be on a geographical fault line, so the bridge may cross a significant seismic or an area with a particular seismic potential. So long span bridges, tall buildings are typically prone to the types of loads that seismic earthquake events would cause a problem. If you were designing in Southern Europe, for example, then seismic would be a much more common occurrence, and therefore would be more fairly represented in codes of practice for designing in that kind of an area, in a seismically active area. If we have a look at ground movement, this bridge that we've designed here might have its initial design as a continuous span over 3 supports, so 2 abutments and a central support here. And as such, the bending moment diagram of this continuous beam would give rise to a hogging moment at this location, a sagging moment here, coming to 0 at this pinned joint here. So you might get a bending moment in this structure with a hogging moment over this central support. Now, if that central support is on ground, which is not capable of providing this reaction load without deflections, if we take it to the extreme, for example, if we allow this central support to deflect significantly, so sink into this ground here, then essentially we lose all or some component of this reaction at this point here. So instead of being a simply supported continuous beam, a continuous beam over this central support, this beam then configures it or reconfigures itself to becoming a simply supported beam that's only effectively supported at these 2 ends. So if we get significant settlements in this foundation and this central support here, we can very quickly completely change the way in which this structure resists the loads applied to it. So we can move, instead of having a hogging moment mid-span and relatively low sagging moments in these spans here, we can sort of push this towards a simply supported structure where we've got a sagging moment instead of a hogging moment at this point, and this hogging moment is this sagging moment is very much increased because we've effectively gone from a continuous span of L, such that the span between the support and the span is L over 2 and L over 2. If we get significant deflections, settlements in this central support, effectively this bridge then is trying to span the full length of L just between these 2 supports here. So you can see it's a very different structure by virtue of the fact that this central support has undergone some kind of settlement or ground movement. So that is a significant design event for structures where the ground conditions are such that we can expect or have to design for the risk of settlement or ground movements in its foundations.